EET 114, Chapter 17, Series Parallel AC Networks, Problem 4 for the network below here. Again, find the total impedance Z sub T. So again, you're given everything in ohms, all right, which means they're already giving you um, the the key to the impedance here. They're giving you the resistive component and the reactive component of each impedance. So what I like to do, and then normally I would write them right on the circuit. Um, you got R1 is 2000 plus J0 or 2000 angle 0. ZC is 0 minus J4000 because it's 4 kilo ohm. So 4,000 angle of negative 90 in polar form. ZL1 is 0 plus J6000 or 6000 angle 90. R2 is 6800 plus J0 or 6800 angle 0. R3 is same thing. And then ZL2 is 0 plus J8000 or 8000 angle 90. So what I would normally do, what I see a lot of students do, is write those numbers right next to each one for visualization reasons. The R's you really don't need to. I mean, they're understood to be plus J0 or an angle of 0, but the inductors and capacitors, you should probably do that. It just makes things easier to visualize. So again, we could see that these three guys are in parallel, and then that equivalent impedance is in series with these two in parallel, and then all of that is in series with this. So the book wrote it out simply the 2K angle 0 plus these two in parallel, which is the 4K angle 90 times the 6K, or I'm sorry, 4K angle negative 90, which is the capacitor, times the 6K angle plus 90, which is the inductor, divided by minus J4K plus J6K. And the reason that why they use the rectangular form in the denominator is because they're going to add them together, and then use the polar form in the numerator because they're going to multiply. But in your calculator, it doesn't matter. You can put them in either way. And remember, when you put these numbers in, you have to put them in parentheses. And don't forget to use the negative sign for this 90. You don't use a minus sign. You use on the calculator. It it it's in the bottom right, and it looks like a minus sign with within two parentheses. It has two parentheses around the minus sign. And then the last part of it was what they did was they took these two resistors, which are in parallel, and since they're equivalent, you can just divide them by 2, because you could multiply them at the top and then take the denominator and add them together. But what it ends up being is just dividing them by 2, angle 0, and then that is also in parallel with this inductor, so that you multiplied it in the numerator, and then in the denominator you take that equivalent resistance of the two resistors in parallel and add to the impedance of the inductor. So once you crunch all those numbers down, they call that ZT prime, which is this portion right here. You don't have to call it that. They're just calling that for clarity. So once you crunch all these numbers down, I recommend doing them in pieces. So you would do this piece first, get this number, and then do this piece next, and they got this number. And then take that and add it all up together, and then you get Z sub t is 4.88k minus J 10.78k equals 11.83k angle of negative 65.64. And then part B says calculate voltage V2 and the current I sub L. So the voltage V2 is going to be across this whole um, impedance right here. All three of these impedances are in parallel, and they're all equal to V2, which is probably why they broke it out and called that Z sub T prime. So they took this piece and found out that it was equal to that 2.88K times J 1.22K. And then they took that, which in the polar form, this is the polar form here. So to get V2, you have to take the impedance that you're looking across, which is Z sub T prime, multiply times the input voltage here, and then divide by the total impedance. So you already found the total impedance, and you found that Z sub T prime. So you just multiply it times the source voltage, which is at 240 angle 60, divide by the total impedance, you get 63 volt angle 148.67 degrees. And then it says find the current I sub L. The way you find I sub L, you know what V2 is across the inductor. You just calculated it. You just divide by the impedance across the inductor, which they called X sub L2. They kind of use those interchangeably. That capital X with bold means that's the impedance across it. You could also call that Z sub L2. So that's AK angle plus 90. And when you divide them, you get 7.88 milliamps, angle 58.67 degrees. And then the last part is find the power factor of the network. To find the power factor of the network, another formula that they have is to take the total resistance in the network and divide it by the total impedance in the network. So the total resistance in the network. Now you might be tempted to start looking at these resistors and try to figure out what your total resistance in the network is going to be. But you already figured that out because here's your total impedance in the circuit right here. Okay, and this is in rectangular form. This is the beauty of using rectangular form. So the first part of this is going to be the purely resistive part. Okay, this is the purely reactive part right here. So you know that the resistive part is the 4.88K. So you divide that by the total magnitude of Z sub T, you get 11.83K. So the power factor is 0.13 or 0.413. So I wrote some notes here for the total impedance Z sub T equal to R plus JX. R is the total resistive component. X is the total reactive component. If X is negative, the circuit is capacitive or ice. So the current leads the voltage. Okay, so capacitive is the C, and then I comes before E, so the current leads voltage. If X is positive, the circuit is inductive, Eli. So the L is the inductor, and then E comes before I, so the current lags the voltage. And then if X is 0, the circuit is resistive.